specific question you want me to discuss? Aman and Sandeep.
Yes, sir. I have some questions, sir.
Yeah, go ahead. Go ahead. I have my screen on, so I should be able to. Let me. Yeah, go on. What is the question?
Sir, what is the physical interpretation of exchange integral? Sir? Exchange integral, because in case of Hund's rule, sir, in case of Hund's rules of maximum spin metricity, actually there also we see the exchange, sir, because when the electrons are occupied parallelly, then they are exchanging, sir, exchanging of electron. So whether this exchange integral and what we are using, sir, in case of that molecular quantum mechanics. So whether both are same, sir, or both are different, sir, because exchange integral actually stabilizes the atoms.
Yeah, exchange integral by itself, to the best of my knowledge, does not have a physical interpretation. Okay, it is purely quantum mechanical in origin, because the wave functions that we use for the molecular orbital are linear combinations and overlaps. They are basically superposition of atomic orbitals, linear superposition. Because of that only we get the exchange integral, where the exchange integral technically uses the coordinate system, the electron 1 versus electron 2, if that's what you mean, the wave functions. But please remember, this is not a typical probability density. If you talk about psi squared R is a probability density, and when you integrate it, it will give you the total electron density. Okay?
Yes.
This is not a psi square R. This is psi R, and another is psi R prime. It's different radii. Therefore, and if you put the Coulombic term in between the 1 by R for the 2 electrons, the origin is purely because of the linear combination that we use. It's very simple. We do not have the eigenfunctions exactly. We do not know the exact solutions. Therefore, we are using an approximate solution, which is exact if we do an infinite linear combination. Okay? If we put infinite number of all the eigenstates with coefficients, then only we have an exact wave function. Even the exact wave function, if you calculate the Coulombic integrals using the basis functions that you are using, like 1s orbital or 2p orbital or 3p, 3s orbital and so on, these basis functions are not eigenfunctions of the problem. Therefore, the exchange integral comes in as a means to correct the total energy by providing this additional energy of stabilization. That's it. There is no physical meaning, the same way that there is no physical meaning that can be attached to the wave function of quantum mechanics. Wave function does not have a physical interpretation. Only the square of the wave function has a physical interpretation in terms of the probability of the particle or whatever it is in that small region. Okay, so since wave functions themselves don't have a physical interpretation, product of two wave functions with two different coordinates connected by the R also does not have a physical interpretation. Okay, does it make sense? Hello? Did it make sense? Sandeep is not there. The others, can you hear me?
We can hear you, sir. We can hear you.
Okay, Sandeep seemed to have gone out. He's the one who asked the question. Did you hear my answer completely, Raman?
Yes, sir.
Yeah, you did. Okay, so there was no break on the internet connectivity. Okay, so I hope that he joins. So, any other questions? Did you? Since you are here, did you find the course useful to you, Rama?
Yes, sir. Yes, sir.
Yeah.
I was
What?
expecting, sir. Yes, sir.
Say it again. Yeah.
Yes, yes, sir. I was expecting mathematical rigor in this course, which I found it, but unfortunately, I'm not. Um, I was not well thorough with this mathematics.
No, no.
So,
You are never thorough with one course one time. Okay.
yes, sir.
You will never
Yes,
be thorough. Okay.
yes, sir.
You
And you recommended that book, von Neumann, Mathematics. Yes, sir.
Yeah.
So
Yeah.
I started reading that book, and I did not enroll for examination, sir, because
Okay. No,
yes,
that's
sir.
all right. That is all right.
Sir.
Yeah.
I am learning this course by self-paced manner, and I also downloaded another book called Special Functions in Mathematical Chemistry
Yeah.
by
Yeah.
Snedon. Yes, sir.
But you, if I recall, I don't think you have asked any questions to me. Did I miss any questions for you? No.
No, sir.
Yeah, you should ask questions. You see, now that you have my email ID and you are also part of this particular program of taking the course, you can always write an email to me. See, what I will do is whenever I have time, I will respond to it. But definitely those who want to learn the subject in which I know a little bit more, I'll be happy to reply. I'll be happy to give some answers. I mean, I need time. Sometimes I may just speak about it for about 10 minutes and then send you the audio or video, how this is being done and so on. So just one moment, very quickly, I'll ask Sandeep Kumar. Sandeep Kumar, did you, I know you don't like the answer because there is no physical explanation, but that's the case.
Yes, sir. Sir, my internet has gone down, sir. My internet has gone down. I reconnected. Sir.
Yeah, but did you hear my answer? You didn't hear the answer at all, right? I told the
initial part I heard, sir. Initial part I heard, sir.
Because the wave function itself does not have a physical interpretation in quantum mechanics. Please remember, wave function is a complex quantity in general. It is not something that explains the amplitude. It's a square of the wave function which is associated with the probability interpretation. And that was done by Max Born. So when the wave function doesn't have a meaning by itself, product of two wave functions at two different coordinates, which is what is responsible for the exchange integral, okay, is not going to give you a meaningful answer that you can visualize. There's no visual ability for this. The number is very helpful to ensure that it contributes to the total energy and the stability of the system. That's all there is to the exchange integral, to my knowledge. Maybe something more than that, but I don't think I know. Okay.
Yes.
Any other question? Raman, you were saying something about you were learning things by yourself. And Sandeep, you are writing an examination by any chance?
Yes, sir. I wrote, sir. I passed net examination, sir.
Okay. Do you find the course useful?
Yes, sir. It is very useful, sir, because it is very elaborate, sir, and very all the mathematical details has been worked out, sir. So it helps in studying all the good books, sir, because we can study. Because in other lectures, many are missing, sir. So it is
you are getting the help to read the good books, I hope, isn't it?
Yes, sir. Yes, sir. Yes.
I think that's the purpose. The purpose is the good books are really good books, but you have to go through them very carefully. And this method of online lectures gives me the opportunity to explain some of these methods more carefully and systematically. But it's a long course. It's 12 weeks, 50 plus lectures. But you can't learn quantum mechanics in 50 lectures, despite all those things. Okay, so I hope it is driving you to read more and look at even and try to understand things. Yeah. So if you recommend that I offer this course again, what would you want me to change to help the students better? Is there anything that you would want me to change and explain things better? Did you find places where you were finding it very difficult to understand?
Sir, sir, in the video lecture, sir, at the time of discussing the hydrogen atoms, actually you have mentioned that you have shared some seeds, sir, some lecture notes.
Yeah.
And those lecture notes are not there, na, sir, because for solving the Laguerre problem, that
They are not uploaded. They are not uploaded in your website.
Yes, it is not uploaded, sir. It is not uploaded.
Okay, I would ask Madhu. Is there Madhu?
Sir.
Yeah. Can you remind me today? I will upload the hydrogen atom lecture notes. It's about 35 to 40 pages.
Sir.
You remember you calculated the L's, the
radial nodes,
7s orbital, 6s orbital, and all those things.
Yes, sir.
So I have added all those things in the lecture notes. So I'll send you that lecture notes with the link, and you please upload it onto the
lecture
supplementary lecture notes. Okay.
Okay, sir. Okay.
Yeah, I'll do that today, Sandeep. Yeah, no problem.
Okay, sir. Okay, sir. Okay, sir. Thanks.
Of you, any other? Okay, we have one more thing now, just now. Subhendu Naik. Good evening or good afternoon, Subhendu.
Good afternoon, sir.
Yeah. Okay. Thanks for joining. Do you have any specific questions, doubts, things that you want to ask? You want to clarify? You're muted. You need to unmute the mic. Okay. So let me just very quickly summarize things for you. Okay. I'll say it in words, but the summary is very important. Anyway, this session is recorded. Balaji, is it being recorded? He's online. So the summary that I have provided in these lecture notes is a very basic one, but detailed in mathematics. Session is recorded. I think so. Yeah, Madhu is asking the question, but if I remember, I should see seeing recording anyway. The important thing about this course is that what I talk to you is preliminary. Though there is a fairly involved mathematics from your point of view, the mathematics that I have used to study the systems is still slightly older and well known in the past, but these days people do not use the differential equation methods, which I put in a lot of time, and also the integrals that I calculated for you using these wave functions. People these days, many researchers use the matrix mechanics and also the numerical programming, mainly because the systems that can be studied using analytical methods and giving analytical results are only those that I have given you. There are no other systems. Okay, hydrogen atom, particle in a box, harmonic oscillator, particle on a ring. That's about it. Those are the only systems. Therefore, any real system like a molecule formation or any complex clusters that you want to study, or the dynamics of molecules in a chemical reaction, all these things involve definitely much more thorough numerical methods and approximation methods, and therefore the algebraic tools that you have learned must be supplemented with a considerable amount of study on matrices and matrix algebra. There are courses in NPTEL which teach you quantum mechanics using matrix algebra. There is also a very famous book by Thomas Jordan on the quantum mechanics by matrices. That's a very small book, but it's a very beautiful book. Thomas F. Jordan, T.F. Jordan, I think if I remember that's the name. I can share that with you in the email today. That talks about matrix methods in quantum mechanics and matrices. Gives you a very nice summary. And those are important for you to understand the next step, the next set of calculations. Also, I have just come up to the point of introducing you variational method and perturbation theory, but I've not taken it up to the real molecular system. That is the next what we call as the advanced quantum chemistry, which starts with these methods and also with the basis functions. But immediately it introduces what are known as the general representation for the orbitals using Gaussian wave functions, Slater type orbitals, and others. And of course, the GTOs, the Gaussian orbitals, are the most famous and most well exploited learning. So you have to learn those things in the next step. What are Gaussian orbitals? How do we classify them? How do we calculate the integrals using Gaussian orbitals? That's the second more advanced course in quantum chemistry. And after that, basically you are a numerical, you start working on the numerical program of calculating molecular properties. So this is one process by which you follow quantum chemistry. The other process is to take this to the molecules in detail and to do analytical methods even more in detail. Very few today are purely analytical in the quantum chemical problems. Most of them follow the numerical methods. Okay. Thomas Jordan, that's right, matrix mechanics in simple form. Thank you, Norman. You have found that out from the net. The Thomas Jordan's book is fantastic. I mean, I enjoyed every part of that book when I studied these things a little earlier when I was a student and I was a researcher. I studied this book. Very beautiful. Okay, that's all I have to say about this because you do not have any specific questions about what you didn't understand or what you did not, what you did. I assume that this course was useful to you. This is my the last live communication for this program. All of you will be writing, those of you who are writing the exam on the 23rd. The exam is not at all difficult, I will also tell you. It is well within what you have studied so far. And I have two more tutorials. The one tutorial which is being corrected now is include this in your solution because you still have another week to do that. The remaining two tutorials that I will add up, you don't need to submit them, but you work them out. I will also provide the answers towards the end of the course. Okay? So you will have 12 weeks and 12 tutorials, but if you have completed 10, we would do some analysis to find out how many have done the tutorials and so on. So I will give some weightage to that. Okay? Otherwise, I am very happy that I had a few interactions with those who are very clear, motivated. This whole process is to find students who are motivated to learn by themselves and teachers who want to use this as supplementary teaching learning in their classrooms. I hope I have fulfilled those two things. Okay. Let me know if there are any other questions. If not, I will wind up this and let you go back to study the course for your final examination. If you have
sir, one, two question I want to ask. Sir.
Yeah, go ahead.
Question. Yes, sir. Sir, I was reading that McQuarrie book, no, sir. In that they have used atomic units, sir, atomic units. So, but sir, I have certain doubts. If we are using the atomic units, then whether we are incorporating all the constants we shall be missing, sir, because when we are using, sir, 1/4πε0 and many other constants we are using, sir. So whether there is any chance that we shall miss those constants if we are calculating all data in atomic units?
So the atomic unit is very clearly defined for quantum chemistry. Okay, it puts the charge, the electronic charge as 1, right?
Yes.
It puts the mass of the nucleus. Which one? Mass of the electron or mass of the nucleus? What does it put as 1?
Yes, electrons.
Electron mass or the hydrogen atom mass? Electron mass. Okay, go back. And
Yes,
speed of light.
Yes.
The speed of light c is also set to 1. And
Yes.
Planck's constant also
Yes.
equal to 1.
H cross is 1, sir. H cross.
Planck's constant divided by 2 pi is also set to 1. All
Yes.
that it does is in that process, it takes the energy. You remember in harmonic oscillator, we had this special definition of x and p, and we took the constants out as h bar omega, and then we had a p square plus q square that we had. So
Yes.
the idea is the energy unit is using these constants is renormalized to the new value called the hot tree.
Yes.
The hot tree, when you connect it to the known energies in kilocalories or kilojoules, you have that conversion factor. Okay.
Yes.
Therefore, the whole thing is exact. There is no approximation, and we don't need anything more to deal with. Whenever we get from these programs the energy numbers, those numbers are in hot trees. Simply convert them using the conversion formula. 1 hot tree is equal to how many kilocalories, and you will get the kilocalories conversion, which is what is measured in the laboratories and in the experiments. Okay. So,
Yes.
yeah, it's accurate. There's no. The idea is to remove these constants. Otherwise, they will be there in all the integrals, and sometimes you may end up making a mistake, deleting some of them, and copying it wrong. All these things should not happen. So we use the atomic units to scale the problem as independent of all the fundamental constants. But then we remember that the final number is dependent on those constants. So at that point, we convert them back. Okay. This is the standard physics method. Okay. Using
Yes.
relative coordinates. Yeah. Dimensional coordinates.
Yes.
Okay. Yeah. What is the other question you have? Yeah.
Sir, in the case of hydrogen plus molecule, sir, H2 plus molecule, we are writing that Hamiltonian operator, sir. The first kinetic energy term for the electron energy, we are writing in the terms of electron coordinate, sir, electron coordinate.
Yeah.
Electron coordinate, and other two are RA and RV from the nuclear distance. The potential terms using that RA and RV, sir, from the,
that's right. That's right. Yeah. What is the question?
Our center of mass, sir, from where we are taking those coordinates, sir, because R theta phi we shall be using.
No, we assume that the hydrogen atoms don't move. Okay. This is the Born-Oppenheimer approximation.
Yes.
So what you are writing is the potential energy, which is constant. That is, it has a nuclear coordinate RAB, right?
Yes.
Which is the coordinate of RA minus RB. Where is therefore the central mass? We assume that these are infinite masses. The approximation, Born-Oppenheimer approximation assumes that the nuclei, being very heavy, have no kinetic energy. Only a mass of infinite mass will have no kinetic energy.
Yes.
Okay? Therefore, ideally, in that approximation, the electron mass, even though it is above, the two hydrogen atoms are somewhere outside of that line, in the central mass coordinates is placed in the middle of the two hydrogen bonds. The two hydrogen connected by the bond, right at the middle. That's because the masses of hydrogen are assumed to be infinite.
Yes.
They don't know. Therefore, central mass is there. Otherwise, if you want to include the kinetic energy of the nuclei as well, then you don't incorporate Born-Oppenheimer approximation. You put the center of mass where for a given R1, R2, and R3, three distances, isn't it? The two nuclei and one electron. So you put 3 distances, you use the mass, you assume that the center of mass is such that we will not worry about the translational energy. We will not worry about any rotational energy, but we will only worry about the bond distance variation, which is basically a vibration, or the electron transition. In that case, what you do is you put the center of mass not on the hydrogen atom, but you actually calculate the center of mass such that it satisfies this condition mi Ri sum over Ri is equal to 0. That's the origin. At that point, we don't do that in general because the Born-Oppenheimer approximation is good enough for most of these calculations. Okay?
Yes.
Yeah. Go ahead. Any other?
And sir, in the case of spin-spin interaction, we calculated that the singlet and triplet partners. a spin interaction between the two spins, sir. Yes, sir.
When there are two spins
Yes, sir.
together, we have now calculated them as singlet energies and triplet energies, right?
Yes, sir.
The triplet energy corresponds to the alpha, and then alpha beta plus beta alpha, and then
yes.
beta beta, if I remember.
Yes. Yes, sir. Yes.
But those are the spin states. Actually, in our calculation for the energies, we do not include the spin energy in the Hamiltonian.
Yes.
If you use the spin energy, you should also correct it, the spin energy, with the spin orbit interaction.
Yes, sir. So, sir, if here we have to find which one is more stable, whether the singlet spin state or triplet spin state.
No,
then,
in the case of hydrogen molecule, the lowest energy will be the singlet state.
Yes.
Both the electrons will occupy the phi 1sa plus phi 1sb square root, 1 by square root, 2 into 1 plus s. So that's the lowest energy. Therefore, the ground state energy for the H2, of course, for hydrogen molecule, not for H2 plus, for hydrogen molecule, the two electrons will occupy the sigma bond, the lowest energy.
Yes.
So it is also zero spin state.
Yes, sir. So, sir, any energy rise or energy decrease with respect to a spin, we are not studying via the Hamiltonian.
You're not including right now. We are only concerned with that's why the pairing energy of the spins we are not considering.
Yes.
If you are asking the question about the spin energy, pairing energy is an example of the spin interaction energy. We don't include them. We only see, if you look at the Hamiltonian has only coordinates of the hydrogen atom and the electrons. It does not have the alpha beta states. The alpha beta states of the spin come to ensure that your wave function follows and the Pauli exclusion principle. It satisfies that.
Yes.
If you want to do an exact calculation, you must also include the spin interaction, the spin orbit interaction to the Hamiltonian, and then your wave function will have all these things together, and then you have to diagonalize that Hamiltonian. That's a different problem. We have not done that. Right?
Yes.
Yeah.
Okay, sir. Okay, sir. Thank you, sir.
Thank you,
sir, one vocabulary, sir, that Brian Macquarie, no, sir, you mentioned, no, sir, Macquarie. So I was visiting his website, sir. So I found entanglement, sir. Entanglement word he often using, sir. Entanglement meaning I never understood, sir. What was
what I said was, entanglement means many things to many people. And in physics, entanglement has a very specific meaning. Now, what it says is that the two electron state, if you remember, let me write this. Okay, maybe I can share my screen if it is permitted. You can see my screen now?
Yes, sir, we can see, sir.
Yes, sir, yes.
Okay, so let me see if I can get my the journal. Hope it's there. Yeah. So you talked about the entanglement. I think I must have mentioned with respect to this state, alpha 1, alpha 2, alpha 1, beta 2 plus beta 1, alpha 2, 1 by root 2. And then I must have said this, the EPR state, alpha 1, beta 2 minus beta 1, alpha 2. Is that correct?
Yes.
This is what I would have said as the EPR state, same as Einstein, Podolsky, states. This is nothing other than the antisymmetric state for the singlet state. Okay.
Yes.
Metric. This is the singlet state. The triplet state contains one more thing, beta 1, beta 2. Okay. That's this. Now, I said this is probably an entangled state. I'm sure I must have used that word. The entangled state means the following. Suppose you measure the spin polarization of the two spins. Spin polarization. Suppose you measure the spin 1 polarization. Okay. in this. Now, what it tells you is that if spin 1 comes out with the alpha 1 state, okay, as the outcome, you remember the spin 2 will naturally be in beta 2 state. Alpha 1, beta 2 is the product of the two spin states. So if the outcome gives you only alpha 1 for spin 1, it cannot give you this alpha 2, it cannot give you beta 1, it cannot give you, because the spin outcome for spin 1 is already alpha 1. Therefore, what is the outcome for the spin 2? It is beta. This is the second spin, this is the second electron, this is the first electron. Okay. Now, the measurement of the state of one spin determines the state of the second spin. The measurement outcome of the second spin. The whole thing is about entanglement, outcome of the second spin. Let's look at the event that the outcome of the spin 1 is not alpha, but say beta. If it is beta 1 is the outcome when you make the measurement, you see the spin of the second spin, the state of the second spin is now alpha. Therefore, you see, you don't need to measure the state of both the spins to understand what is the state of spin 1 and what is the state of spin 2. You measure the state of one spin, you automatically get the result for the next one. Okay.
Yes.
Therefore, the states are mixed in such a way that the outcome for the measurement of one spin determines the outcome for the second spin uncontrollably. You cannot control it. That's what the outcome is. Such states are known as entangled states. Okay. In the quantum literature and in the quantum mechanics as well. This is originally the word entanglement was, I believe, used by Schrodinger. And another example of the entangled state is alpha 1, alpha 2 plus beta 1, beta 2, 1 by root 2. Okay. And the state alpha 1, alpha 2 minus beta 1, beta 2 is another example. They are both orthogonal to each other. This is also 1 by root 2. And the third state, which is entangled, is already, you have it, alpha 1, beta 2 plus beta 1, alpha 2. The minus sign and the plus signs are basically for the wave functions. So to make them orthogonal to each other, that's the complete set. Now you see this. If the state of the spin 1 is measured to be alpha 1, the outcome for the second spin will be alpha 2. You don't need to measure the state of the second spin.
Yes.
You don't know what it is, but it gets fixed to the alpha 2.
Sir, but this is not possible for the a pair of electrons. It is not possible, no, sir.
No, this is for the pair of electrons. This is for the pair of electrons. The spin, this is only with respect to the spin coordinates.
But both spins are parallel, sir, because in a single case.
No, this I wouldn't call it as parallel or anti-parallel. No, that is no longer, that
Yes.
interpretation no longer makes any sense. Okay. When you say both spins are parallel, what you mean is it's a state alpha 1, alpha 2.
Yes.
This is with respect to the magnetic field in the direction Z. Okay. But this state, for example, alpha 1, alpha 2 plus beta 1, beta 2, you cannot say both spins are parallel or anti-parallel, because you are taking the sum of both of them. You are taking the difference of both of them. Therefore, this is a complex state. The complex state in which both the spins are so entangled with each other. It's like, you know, what is entanglement? You have another one twine ball, okay? You get a thread, a twine ball, and you get another thread with a twine ball, and after some time you mix them, and then now you cannot, these two threads are so intertwined with each other that you find it very difficult to take them. They are entangled with each other. Whatever you see, anything that is really messed up completely without any identity for the individual elements. So what it says is the identity for the second spin is determined by the outcome for the measurement of the first spin. Such states are called entangled states, whether it's electron spins or whether it is qubits for photon, two photons, or whether it is for two hydrogen nuclei, spin-a-half nuclei, it does not matter. A spin-a-half system, two spin-a-half systems have these kinds of possibilities. So the same thing, if the outcome for the first spin turn, is not only for the second spin. Suppose you measure the outcome for the second spin and you get beta. Invariably, you will find out that the outcome for the first spin is automatically beta for the state. So whether you measure spin 1 or spin 2 independently still controls the outcome for the measurement of the other spin. That is why they are called entangled. They cannot be separated as products of two one spins. They are not. This is not a product of spin 1 only, a spin 2 only. No, they are not. They are combined with each other. That's what is the meaning of it. Okay.
Yes, sir. Yes.
Thanks.
Okay, sir. Thanks.
Thank you. Okay. So, Raman, is there any other question? Otherwise, I will wish you all the best. You are a self-motivated person to read. Feel free, and Sandeep is very clear that he is going through the details very, very carefully. So I found 2 of you, and there are, I'm sure, many others who may not have come. They are learning in their own way. I hope it helped all of you. So I want to thank you for taking part in the exercise. Okay. So if there are no questions, can we close the session now?
Oh, yes, sir. I'm going to stop the live.
Okay. Thank you, Balaji. Thanks a lot. Okay. So please send a message to all the students. I think Madhu will send a message to all the students. After